Welcome students. So ultimately we have reached to the last lap of our course, which is very important for your course, that is state feedback control design. Okay, so the design of state feedback controller we are going to discuss. So whatever till now we have developed the concepts about the state space representation, you will find that we are going to utilize all those concepts to to design the state feedback control. Okay, so now these are the things we are going to discuss under this topic, that is design of state feedback controller. So first we will start with philosophy of state feedback controller design. Okay, so now suppose we have any linear time invariant system, nth order linear time invariant system, and which is here it is, suppose it is a CISO system. Then the state space representation can be represented by x dot equal to axt plus b into ut, which is known as the state equation, yt equal to c into xt, which is the output equation, and the initial condition, that is x of 0. Okay, so from our previous discussion we know that these equations are vector differential equation, which means that here x is not a scalar quantity. Xt having dimension n by 1 means it is a n vector, and here we have considered CISO system, so we can consider the u is a scalar quantity, and accordingly the output is a scalar quantity. So if you assume like this, then we can find out what will be the dimension of ABC easily. Now most important thing is that from our previous discussion we have understood that dynamic performances is determined by eigenvalues of A. Means if we want to determine the dynamic performance of the system which is represented in state space, then it can be determined by the eigenvalues of A. Why? Now if we comment about the stability of the system, then what we will do, now we will see where the eigenvalues of A are located. If we know that the system is asymptotically stable if and only if real part of the eigenvalues, that is lambda I, strictly less than 0, that is negative for all eigenvalues of A. Okay, so uh, so now that's why A is known as the system matrix, because the characterization of the system can be understood, can be evaluated by the A matrix. So you see the stability of the system can be determined by the eigenvalues of A, and if it is strictly, means the real part of the eigenvalues are strictly less than 0, this condition also guarantees that the system is Bibo stable, because we know that asymptotically stable implies Bibo stability. Not only the stability, if we want to determine the transient response of the given system, that also will be controlled by the eigenvalues, because we know that the transient response is determined by exponential modes of the form tk minus 1, t to the power k minus 1, e to the power lambda it. So these are the elements of the state transition matrix we know. Okay, so if we find out the solution of this system equation, okay, then the solution depends on the elements of the solution will depends on e to the power at, and the elements of e to the power at will be in a general form, that is t to the power k minus 1 e to the power lambda it, and they will determine the transient response. How? Now the shape of the transient response is determined by the location of the eigenvalues. The small modulus value of real lambda I produces slow convergence, while a large real value of the lambda I produces the fast convergence. Means what is the meaning of that? That already I think you have understood. That is, suppose if we have a first order system, simply, okay, simply if we have a first order system, then uh, you know that any first order system will be in the form of what? Now Gs will be in the form of 1 by tau s plus 1. This is the form of a first order system. Now we know that so the pole location will depend at s is equal to minus 1 by tau, okay, where tau is this time constant. Now you see, if we consider it about at pole location, okay, so suppose this is the sigma and this is the j omega. So one pole location we have taken here, suppose minus 1 by tau 1. Another pole we have taken, it is 1 by tau 2, okay. So now from here it is very much clear that if we consider the modulus value of this pole, okay, modulus value of this pole, that is suppose modulus value of S1 is equal to 1 by tau 1 and modulus value of S2 will be equal to 1 by tau 2. Fine. Now from the figure it is, so the pole is located, one pole is located here, another pole is located here, okay, for the, so this is for the system 1 and this is for the system 2. Now if we'll ask that for which case the convergence will be faster, so definitely if the convergence will be faster if we consider the system S2, because its real part is larger than the S1, so the exponential is going to decrease faster in case of S2 compared to the S1. So that is the thing it is told here. A small real part of the eigenvalue produces slow convergence, while a large real part of eigenvalue produces the fast convergence. So that's why previously we come to know that if we will take a very large time constant, okay, for the large time constant, then system response will be slower. Okay, if we will select a small time constant, then obviously the system response will be faster. Okay, so that is clear from this discussion. And now another thing is that a real lambda I produces a monotonic response, while a complex lambda I produces an oscillatory response. Okay, so from this discussion it is very much clear that the eigenvalues of a systems are playing a very important role. Means if we want to determine the stability of the system, then also the eigenvalues are playing a very important role. And if you want to determine the transient response of a given system, that also will be controlled by the location of the eigenvalues. Here you see that real lambda I produces a monotonic response, while a complex lambda I produces an oscillatory response. Means if you consider a second order system, for the second order system, you know that the transient response completely determine the location, depends on the location of the eigenvalues. Means if so if it is sigma, if it is j omega, then we know that if the two eigenvalues are real and distinct, okay, so real and distinct, then we will get that the response we will get, that is overdamped. If the roots are real but they are equal, then we will get a critically damped system. If we will have a eigenvalues complex conjugate in nature, then we will get the response which is known as under damped. And if the roots are located on the j omega axis, then we know that or the eigenvalues are located on the j omega axis, then we will get the oscillatory response. Okay, so then from this discussion it is very much clear that two things, means why this discussion has been made. The only aim is that we to understand that the transient response as well as the stability, everything is determined by the eigenvalues of the system. So that's why here in conclusion it is written, if some eigenvalues of A do not have negative real parts or have negative real parts, but the transient response is not satisfactory, we want to use feedback control to reassign the eigenvalues. Means suppose I have a system that is x dot equal to axt plus b of ut, so it may happen that the system is unstable. Okay, means the eigenvalues, all the eigenvalues of a are not have negative real part. So then demand may come that can we do something with the control ut. Okay, so we will use the control ut by which the closed loop system should have should have the eigenvalues which have all the eigenvalues have the negative real part. Means the closed loop system will be stable. Means that's why can we with the help of control can we reassign the eigenvalues such that the system will be stable. And the same thing can happen, suppose if even if a system is stable. Okay, suppose we have a stable system but the transient response of the system is not satisfactory, then with the control ut can we reassign the eigenvalues of closed loop system such that we should have a better transient response. Means we will reassign the eigenvalues of the closed loop system at the desired location such that we can get a desired response. Okay, because we understood that eigenvalues are controlling the stability and the position of the eigenvalues are controlling the transient response. So the questions now the question we can ask that we want to use the feedback control to reassign the eigenvalues of the closed loop system such that we can have a desired response. Now the question is that how can we reassign the eigenvalues of the closed loop system, that is we are going to discuss. So that's why it is very familiar to the controller design what we have done in the classical control theory. In classical control theory also we have seen that suppose this is the gs is given, now we have to design this kds. Okay, kds, especially this we have to select a suitable value of k, and also we have to find out the position of the poles and zeros of the controller such that we can have the desired pole location to have the desired response. So we add a controller. So this kds is the controller which is added with this system to move the poles to the desired location in root locus design, which we have discussed already, okay, in the classical control design part. So in pole placement approach allows all closed loop poles to be placed in the desired location, whereas in root locus design procedure allows only the two dominant poles to be placed. So in root locus, it means in pole placement we will see that when the system is represented in state space by the state feedback approach or pole placement design approach, we can allow all closed loop poles to be placed in the desired location. So how we will discuss definitely. Now we will you will find that the feedback, this feedback control, the state feedback control can be classified in three categories. First we are going to discuss that is state feedback control. So when we are going to discuss about the state feedback, from the name it has been clear that all the state has to be feedbacked. Okay, so what is you have seen that for a given system what are the states. Suppose for an electrical network, if we assume for the electrical network we have seen that voltage and currents, they are the states. If it is a mechanical system, then position, velocities, they will be the state. If it is a chemical reaction, then temperature, concentration, they will be the states. So now when we want to feedback them, means this temperature, concentration, velocity, acceleration, position or voltage, currents, these are the states of a given system. They, if we want to feedback them, they must be measurable. What is the meaning of measurable? Measurable means there must be a suitable sensor by which all the states of the system can be measurable. So in state feedback, the logic is that all state variables are measured and can be used in feedback. But for the static output feedback, you will find that only some output variables are measured and can be used in feedback, but this we are not going to discuss in this course. And the second thing is that dynamic output feedback, that is using observer. Means if the state variables are not available for measurement, and then also we want to do the state feedback, then what we will do, we will, using observer, we will estimate those states, and that estimated states we will use for the feedback. So the dynamic output feedback we will discuss using when we will discuss the observer, which is the last topic for this course. So first we will concentrate about the state feedback technique to reassign the eigenvalues of the closed loop system at the desired location, and condition is that all the state variables are to be measured. Okay, so some suitable sensors must be there by which all the state variables will be measured, and which will be or which can be used for the feedback. Okay, so now this is the block diagram of the state feedback strategy. So what is the control law? It has been used here, that is U equal to R minus K, okay, into xt. We will come what is K is. So now you see, this is the system, the open loop system. You can consider x dot equal to ax plus bu, and here most important thing is that y equal to x. What is the meaning of y equal to x? Means output is all the state variables, means all the state variable of the systems are measurable. Okay, so y equal to x, the meaning is that that all the state variables are measurable. So now then if the y is equal to x, then you see this x is now multiplied with a gain k, so that's why it is k into xt, and r is a reference input. So then the control which is given to the system, okay, the control input which is given to the system will be in the form of r minus k into xt. Okay, so remember that xt is a vector, so k is no longer is a scalar quantity, it is also a vector. So now we will see what will happen if we will apply the control u equal to r minus k xt in this form, then what will be the closed loop system. Okay, so that we want to understand. So now you see, consider the full state feedback control ut equal to r minus k into xt. So here from this diagram it is clear that why it is called state feedback. So the y equal to x means all the state variables are available for the measurement. So now this state is multiplied with gain k and it is feedback, so that's why it is, the name has been given state feedback. Okay, so now the control law, okay, the control law, consider the full state feedback control law, that is ut equal to r minus k into xt. So now r is the reference input and the gain k is a constant feedback matrix, and its dimension will be 1 cross n, means it is a simply row vector, that is k1 k2 kn, means n number of components will be there. Okay, and its dimension is 1 cross n, means how it is look like basically. So if we will think that the control law, so now the control law is u equal to minus k into xt, and it has been told that k is a row vector, that is k1, its elements are k1 k2 kn. Okay, so its dimension is only one row, and n number of columns are there. Okay, and now if we'll write here u equal to minus k1 k2 kn, okay, into x having how many component, x1 x2 xn. Okay, so if you multiply, the control law will look like, so that is minus k1 into x1 minus k2 into x2, like that, minus k1 into xn. So the control law we are going to design means, you see, x1 x2 xn will be available for the measurement. So now we have to pick k1 k2 kn, we have to find out the values of k1 k2 kn to determine any control law u equal to minus k into xt. Okay, so now here the control law basically is control law is that is ut equal to r minus k into xt. So if r equal to 0, we can call the controller as a regulator. Means if r is equal to 0, what is the meaning of that? If the reference is equal to 0, it means that we want to reach to the 0, means it is a stabilization problem. Basically it will be a stabilization problem. But if r is not equal to 0, means other than 0, suppose r is a step input, then what is the meaning of that? We want to design this k1 k2 kn such that we want to follow the reference input. That is called the tracking problem. Okay, both the things we are going to discuss. So now come to the discussion, that is ut equal to r minus k into xt. So what is the system? System is x dot equal to ax plus bu, where u has been decided that r minus k into xt. So what we will do, we will substitute this u in the state equation. So if you substitute that, then it will be a into xt plus b into r minus k into xt. Okay, so if you rearrange, it will be a minus bk into xt plus b of rt. Okay, so now if you clearly understand that for the closed loop system, so that's why here it is written that closed loop dynamics. Okay, so if you understand that the closed loop system dynamics is a minus bk into xt plus br. Okay, so for the closed loop system, what is the a matrix now? The system matrix, that is a minus bk. What is the system matrix for the open loop system? That is simply a. Okay, but you are finding that if you apply this control to the open loop system, the closed loop system matrix become a minus bk. Okay, which is indicated by acl into xt. Okay, and output will be yt equal to c into xt, and definitely here c is c matrix, all the elements are 1, so actually y equal to xt. Fine. Now if you make r equal to 0, that is also possible for the regulator problem. You will find that this will be the block diagram. Okay, so now you see x dot is integrated, so you will get x, and then this is the system basically, that is x dot equal to ax plus bu. Then if you do the state feedback, then x is multiplied with minus k, and then it is given. So u equal to minus kx, here r equal to 0. So basically here we are talking about the regulator problem or the stabilization problem. Okay, now what the difference make if we will give a control ut equal to r minus kxt? Now that can be analyzed if you see the transfer function, means if you see the characteristics equation of the open loop system and the characteristics equation of the closed loop system. So what is the characteristics equation of the because if you want to find out the eigenvalues of the system, that is the way we can find out, that we will see that what is the characteristics equation of the system, and we'll solve the characteristics equation to get the eigenvalues. So if we want to determine what will be the characteristics equation of the open loop system, then it will be simply determinant of si minus a. But if we want to determine what is the eigenvalue of closed loop system after applying control, then it will be now this new system matrix for the closed loop system is a minus bk. So we will determine determinant of si minus acl. Basically we will determine determinant of si minus a minus bk. Okay, and we have written that may be equal to the s minus lambda 1, s minus lambda 2, s minus lambda n, where this lambda 1, lambda 2, lambda n, where actually we want to place the closed loop poles of the poles, means we want to place the this lambda 1, lambda 2, lambda n are the desired closed loop eigenvalues, means where we want to place the eigenvalues of the closed loop system. Okay, so now we will connect definitely with this k and this lambda 1, lambda 2, lambda n. So remember that this lambda 1, lambda 2, lambda n are the eigenvalues where we want to place the eigenvalues of the closed loop system. But we got the characteristics equation of the closed loop system in terms of k, that is that you see determinant of si minus a minus bk, and we know that and already I told you about the k is a vector of 1 by n. So you will, if you evaluate this determinant, then you will find that a characteristics equation you will get in terms of k1 k2 kn. Okay, and this lambda 1 lambda 2 lambda n, after knowing, if you evaluate this characteristics equation, you will get the characteristics equation of the desired means that will be the desired characteristics equation. Okay, so that's why lambda 2 lambda n are the desired closed loop eigenvalues. Now you see what we can told about this this characteristics equation. The stability and the transient response of the closed loop systems are determined by the eigenvalues of ACL. Okay, that is correct. The eigenvalues of ACLs are called the closed loop eigenvalues, while those A are called the open loop eigenvalues. Okay, so here remember that A is the open loop system matrix and ACL is the closed loop system matrix. Okay, so now what is our objective? Objective is that pick K so that ACL has the desired properties or desired eigenvalues. Means we want to actually determine this K, and what are the elements of K? And the K1, K2, K3, Kn. Means basically we want to choose this K1, K2, K3, Kn such that we should have the desired properties or desired eigenvalues of ACL. Now the question is that how can I pick this K such that we should have a desired eigenvalues of ACL? So that's why the next question has been asked, can we choose K to arbitrarily assign the eigenvalues of ACL? Means if we want to assign the eigenvalues of ACL as per our desire, then can I do that one by choosing a suitable value of K? Because you are finding that the eigenvalues of the closed loop system solely depends on the K. So now the question is that by picking the K, can we place the eigenvalues of the system at the desired eigenvalues, that is lambda 1, lambda 2, lambda n. Okay. Now here I'm not showing any proof, but it can be proved that let A be a controllable pair. Means if we will see that the open loop system will be given, and if we able to verify that AB is a controllable pair and lambda 1 lambda n be an arbitrary set of complex number subject only to the constraint that the complex number in conjugate pairs, means this lambda 1 lambda 2 lambda n may be the complex conjugate pairs also. Okay, then there exists a real 1 by n matrix K such that the eigenvalues of ACLs will be lambda 1 to lambda n. Means it means that if the AB pair is controllable, then we can pick the K1, K2, K3, Kn of the K matrix such that we can place the eigenvalues of the closed loop system ACL at the desired location, that is lambda 1, lambda 2, lambda n. But the uncontrollable eigenvalues of AB, if any, cannot be relocated by feedback. Okay, so that's why very important notion you have to remember. That's why we have discussed about the controllability, that whenever you are going to design the state feedback controller for a given system, then first thing you have to ensure that AB pair is controllable. If AB pair is controllable, then only the controller design is possible. And what is the design? What do you mean by the design of the controller? Means we can pick the gain K1, K2, Kn of K, capital K, such that we can place the eigenvalues of the closed loop system at the desired locations, and they are the lambda 1, lambda 2, lambda n. Okay. Till now, whatever I have discussed, we will try to understand that one by an example. Okay. So now what is the example we have taken? We have taken a satellite system whose dynamics is described by this equation, that T, this torque is equal to the J into d2 theta by d2 t, where J is the moment of inertia of the satellite, Okay, and we will assume that ut equal to t, the torque by the moment of inertia. And if you do that one, then from equation 6 we can write that theta double t equal to u. Okay, means what is the transfer function of the system? The theta s by us is equal to 1 by s square. So this is reasonably accurate model of a rigid satellite in a frictionless environment, and useful in example because its simplicity. So now we have a satellite system whose transfer function is 1 by s square and whose dynamical equation is theta double dot equal to u. Now we want to represent this system in state space representation. So what we will do, now we will assume first state variable is theta and second state variable is theta dot. Then we can easily write that x dot will be equal to ax plus bu, and that is 0 1 0 0 will be the A matrix and B matrix will be the 0 1 u. Here u is missing, u will be there. Okay, so now first thing we have to assume that for the state feedback control, that that x1 and x2 means here you see theta and theta dot, the angular position and the angular velocity are measurable. Okay, now the second thing is interesting, that is this system is stable. Now then if we want to answer that one, then we have to understand where the poles are located of this system. The poles are located both at 0 0. You see the transfer function also we found, that is 1 by s square. So both the poles are located at 0 0. So how it will be now, if you assume that, so this is the sigma and this is the j omega. Okay, this is the j omega, then both the poles of the systems are located here. So is the system is stable? So definitely we know that this system is not asymptotically stable, because none of the means on for the asymptotic stability, all the eigenvalues of the system should be located at the right half of the S-plane, means it should have a negative real part. So this system is not asymptotically stable. Okay, so then if the system is not asymptotically stable, then some control engineers are there, and we have placed one demand to them. What is the demand? Now what the design objective? Now stabilize the system and get a good transient response. Means if we have this kind of system, with the control, you do something such that the system, the closed loop system, will be stable, as well as it should have a good transient response. What do you mean by the good transient response? Now good transient response, that specification has been given. What is that? Now underdamped response with zeta equal to 0.707 with settling time 1 second. Means you should do the controller design U in such a way that the system should have the zeta equal to 0.707 and with the settling time 1 second. Means now the eigenvalues for the open loop systems are located at the origin, double pole at origin. But now our demand is that the system should be stabilized with the control, and not only to be stabilized, you should place the closed loop poles in such a way that the zeta must be maintained at 0.707 with settling time 1 second. So once it has been placed that zeta is equal to 0.707, it is clear from the you know that zeta, when it is in between 0 and 1, where the poles must be located. The pole must be located at the left half of the S-plane, and then they must be imaginary. Means what it means that if this is the pole for the open loop system, now something with the control you do such that the closed loop poles must be located somewhere here, because if you want to maintain zeta in between 0 and 1, here it has been demanded particularly that zeta must be 0.707. For that the root must be located at the left hand side of the S plane, and they must be complex conjugate. And if you place the poles of the closed loop system or the eigenvalues of the system here, the system also will be stable, so both the things will be satisfied. Now if we want to determine if zeta is equal to 0.707 with settling time 1 second, where exactly the closed loop pole must be located. Okay, so to meet this specification, closed loop poles must be located at, we know that for the second order system, root pairs are, the complex root pairs are minus zeta omega n plus minus j omega n root over of 1 minus zeta square. Now it has been told that settling time is 1 second, and from the formula of settling time with 2% tolerance, we know that formula is 4 by zeta omega n, and our demand is that it must be 1 second. So from here we are finding that zeta omega n will be equal to 4. Now you see, zeta omega n is 4 and zeta is given 0.707, that is, you can assume that zeta is 1 by root 2. Then if these two things are given, then you can find out the then you can find out easily what will be the omega n. So omega n can be found, that is 4 root over of 2, and if it is 4 root over of 2, from here we can easily calculate where the closed loop poles must be located, that is minus 4 plus minus j4. Okay, you see, once the design specification is given, we come to know that where actually the closed loop poles must be located. Okay, so it is clear that this is not any pole. Okay, so this must be minus 4 plus j4, and this must be minus 4 minus j4. So it is clear for us. So now for the open loop system, you see the pole is located here. Now we have to do something with the U such that ultimately the pole can be placed in these two locations. Okay, such that we should have a zeta equal to 0.707 with the settling time 1 second, as well as the system will be stable. So now if the design specification is given to you, then it is very easy to calculate where the closed loop poles must be located, that is minus 4 plus minus j4. Means we know that the desired eigenvalues for the closed loop system, that is lambda 1 equal to minus 1 plus j4, and lambda 2, it will be lambda 2, that is minus 1 minus j4. Okay, now if we'll ask that is the closed loop, means if we place the pole in this desired location, is the closed loop system will be stable now? Yes, definitely it will be stable, because both the roots having negative real part. Okay, so now the question is how to place this pole of the closed loop system in these location, and it has been claimed previously that it can be done with the control law, that is u equal to minus kx. Okay, so if it is u equal to minus kx, then we know that here two states are there, so definitely the k will be the dimension of 1 cross 2, so it having two component, that is k1 k2. So that's why the control law will be minus k1 minus k1 into x1 minus k2 into x2. Now the question is that how can I choose this k1 and k2 such that the closed loop eigenvalues will be located at lambda 1 minus 1 plus j4 and lambda 2 equal to minus 1 minus j4. Okay, so now from the previous discussion, it has been told that this is possible, means by choosing the k1 and k2, we can place the poles of the closed loop system at the desired location. It is possible only when this AB pair is controllable. So now we will, for this system, what is the given system is, for this system we will calculate the controllability matrix. We know that BAB is the controllability matrix, and from there it is very much clear that rank of the controllability matrix is full, that is 2. So pole placement is possible. What is meaning the pole placement is possible? Means we can choose the k1 and k2 to place the poles of the system, closed loop system, at lambda 1 and lambda 2. Okay, and the structure will be like this. You see, it is a double integrator. 1 by s you are getting x2, and one again integrating it you are getting x1. So this is the velocity of the satellite and this is the position of the satellite. And to do the feedback, then these two must be measurable, and that they are multiplied with the two gains, that is k1 and k2, and that is the control law, that is minus k1 into x1 and minus k2 into x2. Okay, now if we apply this control law, u equal to minus k into x to this system, that is x dot equal to ax plus bu, then definitely the closed loop system will be x dot equal to a minus bk into x. Fine. And the closed loop system we can write, that is x dot equal to a minus b, that is 0 1, that is k, now k1 into k2 into x. Here the x is missing, here into x will be, and our new A matrix is 0 1 minus k1 and k2 into x. Okay, here x will be. Okay, now so this is the closed loop system matrix. This is the A matrix. Okay, and if we ask you to find out the characteristics equation of the closed loop system in terms of k1 k2, it is possible, because it is simply s square plus k2s plus k1. Directly we can write from here, and we know where to place the closed loop poles, that is lambda 1 equal to minus 1 plus j4 and lambda 2 equal to minus 1 minus j4. So we can, if we know the desired eigenvalues, so we can calculate the desired characteristics equation also. So with this poles, with lambda 1 and lambda 2 are the desired eigenvalues, we can have the alpha is equal to s square plus 8s plus 32. So now this is the desired characteristics equation, and this is the characteristics equation of the closed loop system in terms of k1 k2, and they must be same to have the poles at minus 1 minus 4 plus j4 and minus 4 plus minus j4. So then if you compare these two characteristics equation, then we are getting that the gains are k1 equal to 32 and k2 equal to 8. Okay, so in this way we can determine that k1 k2, and this is the control law, ut equal to 32 minus 32 x1 and minus 8 into x1, and if you apply this control law, then the closed loop system definitely will be 0 1 minus 32 and minus 8, and if you calculate the closed loop characteristics, closed loop pole location, obviously they will be minus 4 plus minus j4. So means with this gain k1 and k2, we can place the poles of the closed loop system at the desired location, and that's why this design procedure is known as pole placement design. So we want to place the poles of the closed loop system with the selection of proper controller gain, that is k1 and k2. And also you have understood, I think, that why this technique is known as state feedback design, because we require the information of state, both the states x1 and x2, to implement this control law. So that's why this technique is known as state feedback design. Okay, so now we can summarize what we have discussed till now with this example. Okay, what is that? And this technique for the finding k1 and k2 is possible, or it will be convenient if the order of the system is less than equal to 2. What is that? Now for the step 1, what you will do, now select n eigenvalues lambda 1 lambda n of the closed loop system, and if they are complex, their complex conjugate is included. Means these are the desired eigenvalues where we want to place the close, that must be known, and that how it can be determined in your exam. It can be given directly, or some specification like the example will be given, like the zeta will be 0.707 and the settling time will be 1 second, or it may be given in terms of percentage of overshoot also. So some specification will be given. From that specification you have to evaluate where the desired eigenvalues must be located. Once the desired eigenvalues will be given to you, you can calculate what will be the desired characteristics equation. Okay, so that is your actually closed loop characteristics equation. That is lambda alpha s is with the lambda 1 lambda n, and that is s1 alpha 1 s to the power s minus 1 and then alpha n. Okay, here definitely this alpha 1 alpha n are the real numbers. Okay, now you know that the form of the feedback control law will be u equal to minus kx. Okay, and if it is u equal to minus kx, and if you apply this control to the system x dot equal to ax plus bu, then you know that the closed loop characteristics equation of the system with this kx will be determinant of si minus a minus bk. And once we will get this as in terms of k1 k2 kn, then you compare with the alpha s with this sorry, here it will be aks, it is aks, then you can find the value of k easily. Okay, so here it will be aks. So now from here it is very much clear that how the process of pole assignment can be done if it is n less than equal to 2. And next we are going to discuss for the pole placement design for the higher order system. Means if the order is n greater than equal to 3, then n greater than equal to 2, then how we can design this pole placement design, or how can we pick this k1 k2 kn for a given system with the desired eigenvalues, that we will discuss next with the transformation technique. Another is using Ackermann's formula. So these two we are going to discuss in the next class. Okay, thank you.